Welcome. In this lecture, which has multiple sessions, we'll explore how to write the Lagrange function using what's called the dual formulation. The main concepts for this lecture are that the dual formulation first finds the Lagrange multipliers and then solves the optimization problem. The minimizer is deduced from those multipliers. The Lagrange function is very commonly expressed as a dual problem. And our sample problem for this lecture is how can we solve for equality constraints using the minimum number of possible variables. Let's recall from a previous session a property of gradients. Let's recall that at a stationary point, so at a stationary point of an objective function that has a vector argument such that a single property function was satisfied at that stationary point, that the gradient of the objective was equal to minus a multiplier mu of the gradient of the property at that stationary point. We can, if we look at this, what we see is a partial differential equation. These are partial derivatives and they're equal to a multiple of some different partial derivatives. Now an infinite number of functions will satisfy this condition. One that satisfies it is the Lagrange function. And the Lagrange function is more or less integrate both sides and then add them. And this is usually a script L, and it has W, and in our case we're only examining for now one property, and that will equal by definition the sum of the objective and some scalar multiple of the property at that objective. So our basic unconstrained problem is this. What we want to do is we want to find a stationary or a minimizer, and that is the minimizer over of the objective over all vectors that are in the vector space. What we could do is we can add, in this case, one linear equality constraint. So this property function, let's suppose that it is a one form times the stationary point minus some constant has to equal 0. What we could do is we could say, well, because we want to find the minimum with this condition, couldn't we just restrict this search to be over the vectors that already satisfy this condition? And that method is called a feasible set method, and it's an important one both in general in optimization, but also it will help us to understand some of the things that are about to go on in subsequent sessions. So we could define the feasible set as the set of all vectors in the vector space such that this constraint was satisfied. And we could then reformulate the problem as the optimal point is the argmin of the objective, but now instead of allowing the vector to go over the entire vector space, we could say that the vector has to be only in that feasible set. And when we do that, what we're doing is we're saying let's take this constraint and let's plug it in. So this is one idea, is that we can reformulate this optimization problem. One reformulation is as a feasible set. And as I said, there are lots of methods in optimization that rely on restricting to a feasible set. What we'll do in the next session is we'll try to take a different view of it, and we'll say, can we reformulate this in yet another way?